Hi, my name is Søren. Welcome to this video about Morini front suspension with a specific look on damping. What I'm going to talk about of course also applies to any other front fork that has the same design. So if you have a Ducati or a Guzzi or even a Japanese bike with a front fork that is made the same way, you of course can use this information also. Our Morinis have very good handling. That's a known and indisputable fact. And maybe that's the reason why most Morinisti only talk about tuning the engine. But the fact is that Morini has so many flaws. The frame is too floppy, the swing arm is too short, and is also too floppy. You can find numerous things that are far from perfect with the Morini. But in the end, this cacophony of flaws magically all go together very harmonically. So you actually have a bike that handles so well that you can keep up even with modern bikes if the roads are twisty enough. But there is room for improvement. Some of the things are quite invasive. The frame is hard to do anything about. Of course you can get a swing arm from that era, these tuning parts, for example from Rebound, which is much stiffer and a bit longer. And you also see people buying rear shocks with modern specifications, but you rarely see anyone doing anything about the front fork other than experimenting with different viscosities of the oil and changing the oil level a bit. There is actually a very simple and rather non-invasive and inexpensive solution that will improve the front fork immensely. And that is what I'm going to talk about in this video. So what is the purpose at all of having a suspension? Originally, and of course that's still the case today, you want to have a comfortable ride, so your body won't be exposed to these hard bumps. But when we're talking about handling, the main focus is to have the tire sticking to the road surface under all conditions and at all times. Almost all modern motorcycle suspensions are made up of two elements. A spring that will absorb these bumps and release the energy so the wheel will return to its original position, and a damping unit that will control this movement. If you don't have damping, a spring will oscillate until it settles, and you don't want that because every time it oscillates you have diminished road surface contact. Our Morinis have what is called an orifice damping, which is simply a fancy word for oil or liquid passing through a hole. So with the different thickness or viscosity of the oil, or with a larger or smaller hole, you control the rate at which the oil passes this hole. Let's have a closer look at how this 35mm Marzocchi front fork is made and how it functions. On page 90 in the manual, you'll find this drawing of the front fork. When we're talking about damping, the essential parts are those, and they make out the damping unit. That is what I have here on my desktop, but with only the essential parts when we're talking about damping. The screws, circlips and things that hold it in place have been removed. That leaves only the damper rod itself with the seal and the rebound valve. That consists of three parts. The damper rod is mounted in the fork leg, and the rebound valve is mounted in the fork stanchion. As I don't have the skills to make a fancy CGI animation, you have to bear with this crude model I've made. With this I'm going to try to explain how the damping works. This is the fork leg, this is the fork stanchion. What we have here is the damper rod that is mounted inside the fork leg, and this represents the rebound valve that is mounted to the fork stanchion. It's a one-way valve that will primarily only lead oil upwards. This is the oil level. The oil level has no importance for the damping. The only thing you need to be sure of is that the damping unit is submerged in oil. When you talk about oil level, what is important is actually not the oil level itself, but the amount of air on top of the oil. The air will act as a spring when compressed, and together with the actual spring, you'll have the total spring rate. But I won't go into details with that because this is all about damping. When we look at the assembly, you will see it sort of forms three chambers, and I will call them the upper, the intermediate, and the lower chamber. If we look at the intermediate and the lower chamber, you'll notice that when they have the same length, the volume is smaller in the intermediate chamber than in the lower chamber. And that is important for understanding how the damping works. Let's have a look at how the compression damping works. You hit a bump and the fork leg moves upwards. The pressure rises in the lower chamber because the chamber gets smaller. The valve will open and the oil will be forced up to the intermediate chamber. But because the intermediate chamber is smaller than the lower chamber, there will be an excess of oil here, and it has to go somewhere else. And for that, there is a hole in the damper rod, in the lower part of the damper rod. So this chamber will of course get filled, and the rest will then move up through the damper rod and to the upper chamber. And that is actually how the damping works. It's the rate at which the oil will pass through this hole that gives the damping. With the smaller hole you will have more damping, with the bigger hole you have less damping. Rebound damping works like this. The leg moves downwards, the valve closes. Of course, this chamber gets smaller. And the way you get the damping is by controlling the rate at which the oil will pass to one or the other chamber. With our Morinis, the valve simply doesn't close completely, so it will let some oil pass by, and that is what gives the damping with our rather simple Marzocchi front forks. Another way is to have the valve close completely and then instead have a small hole on the top of the damper rod. And the size of the hole of course will then determine the damping rate. Now, what is the problem with our primitive front fork? There are several problems, and if we look at one of them, there are different demands to the compression damping than there is for the rebound damping. If we look at the rebound damping, the object for the suspension is to have the wheel and the tire as fast and as controlled back to the tarmac as possible. So when you hit a bump, you want the tire to cling to the asphalt after you've passed the bump. The forces that the damping needs to deal with are the forces given by the spring. On the other hand, the compression damping, it has to deal with whatever the road surface offers the suspension. So if you hit a soft bump with slow speed, this leg will move slowly. And if you hit a square bump or with high speed, it will move fast. The media we use for damping is of course an oil, a liquid. If you've ever played with water, you might have done this experiment. If you put your hand on the water surface and relax your muscles, your hand will simply float calmly towards the ocean floor. But if you smack down your hand on the water surface, you have experienced that the water becomes almost concrete-like. And that's the same problem we have with damping. When we had these soft bumps, it's like letting your hand go. But when we hit these hard bumps or square bumps, the damping becomes concrete-like. You might say, well, I'll simply adjust the damping so I at least have a comfortable ride with these hard bumps. But that will give you less control over the low suspension travel speeds, because the spring will simply oscillate. On the other hand, if you do it the other way around, you of course then will have this hard suspension, and you will again have less control over the wheel because it will simply fly over the bumps. So what can you do about that? Ideally, you would have a self-regulating system that would adapt itself to the varying speeds of the suspension. And since the viscosity of the oil is a fixed value, the other option is to have the orifices change in size. So when you hit these fast bumps, you have a larger hole, and for the slow movements, you have a smaller hole. Of course, both the compression and the rebound damping has to deal with varying speeds of the suspension, since the energy of the spring will be released for the rebound damping. But in reality, the compression speeds are up to 6 times faster than the rebound speeds. And that is why you can actually get by with a simple fixed value for the rebound damping. It's not ideal, of course, but for road use you can get by. For the compression, you will have a huge advantage with this self-regulating system. And there actually is such a system that can be retrofitted our old primitive front forks. This is a cartridge emulator valve. It has its name from mimicking or emulating the cartridges you find in modern suspension types. It's a small 2-valve unit, 2 valves that open in each their direction and that have 2 different properties. The cartridge emulator valve is placed on top of the damper rod, and its function is to replace the original compression damping and leave the rebound damping as is. That's the reason for this valve. It has to open so the oil will flow freely and not influence on the original rebound damping. For the compression damping, we want the control with the small valve, and for that you have to drill more holes or make these holes bigger so the oil will flow freely up to the valve. The valve has a small hole, and that takes care of the low suspension travel speeds. You will simply have the damping through that hole. When the speeds pick up, the pressure rises and the valve will simply be forced open accordingly. As you can see, you can adjust the preload of the valve so you can regulate when it has to open. And of course you can also replace the spring with a softer or a harder spring. So you have plenty of adjustments with this emulator valve. So there you have a self-regulating damping system that adapts itself to the different suspension travel speeds. You might have figured out that it has, or rather both of them, because there goes one in each leg, they have to go out of the front fork in order to regulate them. And I think that's the only drawback about the system. The way you regulate the damping is that you first make sure that the rebound damping is correct, and that you do with the viscosity of the oil. When that is in place, you regulate the compression damping. What you see here on my desktop is an alternative to the original damper rod and rebound valve. The original system has some design flaws, and this design here deals with these problems. And at the same time it's made for use with the cartridge emulator valve. The design is Paul Compton's, so once again I have to thank him. The problem with the original system is the rebound valve. It's a simple washer that seals up against this seat, and when it's open, it's the valve is the washer is forced up against this other special washer. The way the valve doesn't close completely, as I talked about earlier, is that the hole in the washer is a bit bigger than the diameter of the damper rod, and that way the oil can pass by. Because the valve, this washer, can move freely, it has a tendency to scrape against the sides of the damper rod, and as you can see with this one, it has quite some wear marks. So all in all, it's not the most precise or durable design. The alternative is a valve that won't wear out the damper rod and will close completely, and instead the damping is controlled by two small holes. There are two additional problems with the original damper rod in connection with the cartridge emulator valve. The oil has to flow freely from the damper rod to the valve, and this nut will restrict that flow. And at the same time, these two parts have to seal tightly, and they don't. One solution would be to have a spacer of sorts that would create a distance, so that would be a better flow around the nut here, and that this spacer at the same time could act as a seal between the two parts. This is what the alternative damper rod actually forms. It creates a distance and a seal at the same time. An additional part is this emulator sleeve, and it deals with the way the spring and the emulator valve meet up. It creates a distance between the spring and the emulator valve, so there will be a better flow around the valve. And at the same time, it makes sure that the spring doesn't damage the cartridge emulator valve. If you would like to make a damper rod and valve yourself, and this emulator sleeve, you can find the drawings on my homepage. If you don't have the possibility to make them yourself, I sell them. So if you're interested, write to me. The email address is at the end of the video. Of course, this is not a plug and play solution as such. You need to have some sort of solution on how to place the cartridge emulator valve on top of the damper rod so they will seal tightly together. The simplest solution I would suggest is a simple spacer. But since the valve design isn't the best one, a better way is of course to have a complete new damper rod. Cartridge emulator valves are a simple and inexpensive way of getting huge improvements of these orifice damped front forks. If you would like to immerse yourself in the subject, get a hold of this motorcycle suspension Bible from Racetech. Racetech are the inventors of these cartridge emulator valves, and you'll find all you want to know about suspension in this Bible. I'd also recommend you have a look at Dave Moss's YouTube channel. Dave Moss has spent his whole career setting up motorcycle suspensions. And he used to be a Morini rider, so he's one of the guys. I'd of course also urge you to have a look at Paul Compton's YouTube channel. If you have any experience with setting up the suspension, and especially with these cartridge emulator valves, with which I have only limited experience, I would very much like to hear from you. To me, it's much more interesting to go 2Ks faster around the corner than having a 20k faster top speed. All the information I've been talking about, these links, you will find in the description of the video below. And again, if you're interested in these damper rods, write to me. Thank you very much for watching, and happy cornering.